Okay, so hello everyone. So I'm Matthias. I'm currently a postdoc at NYU in Stefano Martiniani's group. And today I want to tell you about a recent interest of mine in disordered materials, which should come in full screen in a minute. Should it work? Well, if it doesn't work, just never mind. Oh, okay, cool. And first start, I want to ask you to imagine your ideal material for whatever application you have. And in most cases, I believe that you will imagine materials that have some form of what I would call long-range correlations. Here, I mean that in a very loose sense, just correlations at a scale that's much larger than that of its constituted elements. The most paradigmatic example of that is crystals. Crystals are great because they have a lot of interesting properties, electrical, mechanical, thermal, and others. And I want to argue that this is because they have correlations that survive all the way to the scale that we see them at. So this great pyrite crystal over there actually shows a cubic structure because it has correlations at that range, at the range of like an inch. But crystals are also a kind of ordered structures I don't really like, in the sense that, sure, it's cubic, but it's also cubic all the way down to the atomic scale. It's periodic at the atomic scale all the way to our scale. So the question I want to ask is, can I actually design materials that are interesting due to their long-range correlations, but that look otherwise as disordered as possible at smaller scales? And one of the reasons for that question is basically that it does exist in nature around us. You may know that the color blue actually is very hard to make if you're an animal, because there are very few bioavailable blue dyes that make blue by absorption. So a lot of animals actually found a way around that by making structures that have some form of correlation that makes so-called structural blue, meaning that it will just reflect light in such a way that you will see blue when you look at them. Be they birds, mammalian skin, or insect scales. So now the question is, okay, this exists. Can I actually produce whatever function I want as correlations that you may see there? These are clearly not crystals, but also they are clearly not completely random. Can I make interesting correlations like this? And long story short, the answer is yes. And we developed a fast algorithm that's orders of magnitude faster than fast implementations that lets us actually impose spectral correlations, so features in the structure factor of a point pattern, up to very large sizes. So we played a lot. We made searches that were disks of zeros, ellipses of zeros, checkers of zeros and ones, or basically anything we wanted, as long as it was center-symmetric. So a very good example of a center-symmetric shape we could impose was a playing card, where I want to insist that here we only impose features in the center, but everything else is left free. So there is a funny optimization game there of letting the system do whatever it wants otherwise. And this is a very small part of the point pattern that we make. So now, what did we make that could be useful from that? Well, you have to actually be limited by your imagination at some point and be like, okay, I can do that. What do I want to make as an interesting material? And I want to argue that an interesting structure is a structure that has G regularly spaced peaks on the ring in the structure vector that are as high as possible. The first question is, can you actually make that? And well, I let my algorithm decide for me, yes, it's possible. And then what you get is a funny structure like this, where if you look at any point in there, and you look at the structure around it, it's pretty unremarkable for some time, until you reach a typical distance that's decided by where you put your ring, where what you have is G regularly angularly spaced points there on this one ring, but with radial fluctuations. If you look at the final structure vector you get, which is here, I insist, in log scale, so that the main features here are much higher than the rest, you get the picture imposed, some echoes, and then basically nothing else. It's very disordered far away, and it's not ordered much in the center either. And the picture I like a lot here is looking at the pair correlation in real space of these structures, which show you that, indeed, it's isotropic neighborhoods all the way to the distance that corresponds to where your peaks, where isotropy breaks down and you have these structures. So now, why did we make that? Well, come to my poster and I'll show you that there are good bandgap materials that are pretty isotropic. And with that, I'm done. Thank you.